Now we are live, folks. That's right. We're broadcasting on this Internet of Stuff and Things. We're here with Jen today from the Church of Entropy, and we're going to be going over some of her work on Gauss's theorem, as well as potentially some other physics and math-related things. You all know what that means.
Though I know I should be wary, still I venture someplace scary. Ghostly haunting, I turn loose. Beetlejuice! Beetlejuice! Beetlejuice!
Hey guys, what's going on? Memes here. And again, I'm here with Miss Jen from the Church of Entropy YouTube channel. Since we've done the intro now, say hi to the good people, Jen.
Hello, everyone tuned in. Thank you so much for being here today, and thank you, Memes, for hosting.
All right. There is a lot of excitement going on within the physics community. We have geometric unity. We've got the potential vortex solution for stuff and things. And we got one of my patrons, Joe Franco. Hail, Joe. How are we doing, my friend here? Shoutouts to my patrons, Joe Franco and Dave M. This broadcast is helped made possible by viewers like you, and things might be getting a little bit more interesting soon. We'll go into that at a future date. But Jen, you've been doing some work. You mentioned something with Gauss's theorem and something about maybe mapping out some very weird shapes that we don't really understand. Enlighten us, please.
Yeah, so you remember the show last week, 7 p.m. Yep. Sunday Eastern, Week in Review with the one and only David. We were talking about the theory. And you, as usual, were being a very positively contributing member of the community. And we got into some of your areas of interest, which led me to realize that the Gauss theorem, the basic idea behind the Gauss theorem, is itself something I can predict using my model. In other words, using the mechanism of entropy. So for the people who aren't too familiar with how physics has been going, that the domain of statistical thermodynamics, which largely deals with entropy, that's basically been exploding since Boltzmann's time, which really wasn't that long ago. So Boltzmann, if you look him up, he got a lot of flack for his theory because it sort of went against the dominant metaphysics at the time. And he actually ended up taking his own life in the end. But what he did really laid the groundwork for a considerable chunk of what is taught as physics today. So when I did my degree in physics, I took 2 courses called thermodynamics, and those were required courses. So if we pull back even more and look in just a generalized domain of physics, we see sort of several different approaches, right? You have your standard model approach, which is going to be looking to reduce everything to the action of quantized particles. And then you have the quantum theory, which is sort of summarized by the Copenhagen interpretation. Right, and then you have entropy as well. And we sort of know that entropy is operating, but it has not really been unified, i.e. entropy and quantum mechanics don't really have a huge overlap. So that's what I have attempted, that's the gap I've attempted to bridge with my work. So I am not looking to validate the standard model. I'm not looking to work within the confines of the standard model. What I've done is a complete bottom-up approach. So I've gone through the results of science over the last 200 plus years, because you do have to go back quite a bit just to see the stuff that we're learning even still today, and then looked at every single argument and axiomatically decided which ones I was comfortable using in a theory. So what am I 100% sure exists and is not just some artifact of a measurement device, right?
So you're going back to times where it's like, all right, we know, as far as we know, this is true, because you mentioned the Copenhagen interpretation, which, from what I remember from physics history, was a whole bunch of scientists had a big disagreement. I believe it was Niels Bohr and what was the other dude? I forget. But we ended up going with a particular interpretation, and there wasn't 100% necessarily agreement there. So,
well, I mean, I don't think they got everything right, but I think for a first effort, they did a really good job.
Right.
So what they were basically trying to do is axiomatize quantum. So
Okay.
what are
What
we
does
just
that
going to
mean?
assume is true when we
Right.
approach these quantum systems, which by virtue of their connectedness with their measurement devices, that we can't necessarily isolate the point at which the measurement device ends and the measured entity begins.
Okay.
But what they tried to do was say, well, even though we can't really, even though we will always struggle with the subject-object dichotomy, we're going to put in these guidelines, which are, some of them can serve as axioms. So for example, the equivalence between waveform reduction and observation or measurement. So I think the way they word it is, in order for a waveform, waveform reduces to one of its eigenstates when it undergoes measurement via a device.
Right.
I think that's an axiom, right? Because you're affirming something about the system, which is unfalsifiable.
We are attempting to measure something, often using devices that have some form of energy associated with them, and by doing something to something that is so finely tuned per se, all of a sudden we might not be getting the whole story, or it's very difficult to have all the parameters basically defined there, because when we're doing something, we are actually kind of like tickling the system, and it goes
Yeah, think of it like this,
exactly
okay?
like that,
Think of it like this. So we'll start with a super simple example. Okay, you're a biologist and you want to look at a cell. What do? Grab that microscope and your tincture and whatnot, throw it on a slide, and you observe it, right?
Right.
The fact of you doing that is not changing the material nature of that cell in any appreciable way.
Mm-hmm.
The only way you could argue is, well, some photons had to bounce off that cell in order for them to register in my eye, correct? And maybe one of those photons destroyed something in the cell, right?
Ooh, yeah.
So even then, we have this tiny little asterisk that we're not actually looking at. We're not actually observing the cell. We're observing photons that bounced off the cell. But that's not really an issue, is it? But it becomes an issue when we're not even sure what the measurement device is doing. So we can be reasonably certain, because we've got all this lens science, huge corpus, right? We know what's happening. We know there's some light. We know it can be modeled in a particular way. And we know that based on these diagrams of lenses, we can create an image, which is going to be a magnified image of the original cell, right? That's not...
You're saying
something...
things are going to change depending on how big or small they get?
Well, what I'm saying is that we don't need to invoke quantum effects to understand the mechanism of looking at a cell under a microscope. Right. Because we're not the only manner in which we are materially exposing the cell to change is the photons themselves, or whatever the cell is sitting in, right? But our looking at it isn't probing it, but for the photons, which we sort of acknowledge are there, but we say, well, that's just the error bound, right? The system's going to have some noise, right?
Well, I mean,
we can basically write that off.
Scale. Well, we're at a particular scale. How much are those photons doing to that particular cell that's going to affect our observation of the cell? It's going to do something.
And what we're saying,
but for the most part, it's
nothing. We're saying it's approximately zero. We're acknowledging that it's not zero, but we're saying that for the purposes of looking at the cell right now and finding the wall and whatever we're looking for, it doesn't really matter, okay? Because we can, it's there, but it's not materially affecting the system, right? Because if it was, by virtue of looking at it, the cell would change visibly, and it's not doing that, right? So whatever changes are not big enough to actually change the interpretation of the result. But if you get to something like electron slit experiments, so are you familiar with a basic setup of an electron slit experiment?
You get those double slits and everything. You go
it's
through
just
there.
One. It's just one slit.
Okay.
There is a double slit experiment, but in this case, I'm just talking because I don't want to go into confusing. So what I might do is share my screen.
Okay. We're gonna do that.
And let's see if I can get this going. Oh no. All right. So I want to share. There we go.
Welcome, Parrot Head, as well. as well as Dave joined us as well. Thank you, gentlemen, for joining.
Thank you to the audience for joining. Memes' Patreons really appreciate that. That's awesome. Hope you guys get something out of this. There's a little meme I made.
Oh, okay.
That's just an opener. That's not actually what I wanted to mention.
Is that Heisenberg?
It's me. Like this me. The name of this meme is, oh my god, that's literally me.
Oh, go on.
Well, can you see? I don't know if you can see it, but
I can see it. I can see that picture. That picture actually looks familiar from a presentation I watched the other day. But continue.
Well, I won't explain the whole meme. I don't want to derail the combo, but I'll show you. Okay, so here's an example of what happens when, because the way this is set up is you have a gun that puts out a single electron at a time.
Mm-hmm.
In front of the path of that electron, you have a slit, a single slit, and then you have a screen that these electrons will eventually collapse their waveform energy to. And so B would be the example where, a low number of electrons have gone through. So at the point of B, it appears to be completely randomized. Would you agree?
Oh, okay. So that is the measurement device.
The measurement device has two parts. It's very important to remember that the measurement device has two parts. It has a slit and a screen.
Right. Okay. So we're viewing the screen after effects.
Exactly. So if we look at B, I think we can pretty much say there's no discernible pattern in that.
When we get to D.
I would say by the time we get to C, there's a pattern.
Yeah.
You can see the bumpiness, right? Definitely by D. And by E, you can see it's a very clear, what you call a periodic waveform. And what this is basically saying is that within the electron and the slit, it's somehow able to give us a distribution. Whereas if there was
we have
no
a 600-pound gorilla joining us. Welcome, Tom. I think what Jen is trying to say is, when you put a bunch of energy out there, it ends up forming in some form of a wave, bro. That's what I'm getting.
No, what I'm getting at is, what I'm trying to build up to here is how the measurement device interfaces with an electron. Because if there was no slit, what would this look like if there was no slit? What would this screen look like if there was no slit?
Oh, that's right, because it's only going through that very small focal point right there. And since it's going through that focal point, it ends up doing that. So if that focal point isn't there, okay, continue.
Well, what's the answer? If there was no slit, what would happen? If I had a gun pointed straight at a screen and there was no slit, and I periodically I shot out individual accelerated electrons, what would the pattern be over time?
I mean, we assume it to be fairly straight, or maybe something, maybe a little spirally. I don't know.
A dot to within the uncertainty of the gun.
Is that what happens?
Well, of course. If you don't obstruct the electron with a slit, you get everything registering to within a circle, which corresponds to the uncertainty of the gun. Because you got to remember, the gun is also itself a physical system subject to uncertainty. It can't do perfect accuracy, so it's not going to be a dot. It's going to be a little blob where that represents the uncertainty of the gun.
Right. It's basically, it has a certain level of uncertainty, but more or less you're hitting the bullseye or within the greater bullseye area, as long as nothing else has changed.
Because the way to think about it is, what's nature? It's spheres. What are photons? They're spheres. What are we trying to generate? We're trying to generate a non-sphere from spheres. Well, that means we're going to have to focus the shit out of it, which means that it's not going to be a perfect process, because we're just like, doing our best to kind of jam that signal into one focused point, right? So that's a bit of a digression, but these things are important because it all informs subject-object dichotomy. Where does measure and where does observer and observe, where's the boundary? And that's the real challenge of physics. So the idea here is, go ahead.
My one question is this how zebras got their stripes?
Yes, absolutely. That's what you call a trace of a standing wave.
Cool.
All right.
And Tom, the real answer might actually, you might actually like it, because I hear a lot of water referred to in certain things I've heard recently. But continue, Jen.
Can you see the diagram I've got up there now?
Yep.
So we have our Platonic pure form. We can deduce the
Okay.
electron is going to be a sphere if it's unperturbed. Okay. So we always start with, when we're building up the logic, we start with monad, free space, observation device. So we start with the absolutely perfect version, and then we modulate that according to the system configuration. So what this result here has allowed scientists to infer is that you have quantization of the moment of the electron. So it doesn't have all possible momenta. It only has a certain number of momenta corresponding to LZ.
So does this kind of mean, given that tiny little bit of uncertainty within the actual electron producing...
And remember, it's not uncertainty. It is, well, how would you say it? It's the
Error.
No. It's the Schrodinger wave equation having energy in multiple eigenstates. Okay, because observation, what does it do? Collapses to a single eigenstate. So what is the state of the system before observation? A bunch of eigenstates, a probabilistic distribution of eigenstates, the sum of those being 100. And it is the action of observation which jams the total energy of the system into a single one.
So what you're saying is, when we're essentially observing, we muck around with those electrons and kind of distort them.
Exactly. So when you're driving your car, you experience continuous increase of momentum. Yes, you can push the gas, and it's, it's not like you're going from 0 to 60 and not doing every single intermediary speed, right? You must pass through every intermediary speed before you get to 60.
You're transitioning to that particular velocity.
But the electron does not operate on that principle.
Oh,
so it only
kind of like our version of a balloon. It's like you poke it with a pen, something happens. Okay, that's a bad analogy.
Well, it would be like a balloon balloons. If the balloon couldn't pop, because the electron can't pop.
That's probably good.
But it is very balloon-esque, because you think of like a sphere being shot out through a gun, encountering a slit that has a smaller volume than the waveform itself. So the balloon, what does it do? It reaches, so imagine like being a big, giant, overweight person trying to fit through a teeny tiny door. What do you have to do?
I mean, hopefully the door is large enough and you can get some exercise and stuff. But typically, if something don't normally fit through there, you kind of got to squeeze. You seem like a big guy. Imagine trying to get into the smallest car of all time. You would have to contort yourself in some way, right? It's the same with the electron. It's just that the electron's ability to, quote, bend over is restricted to within a very small range of eigenstates because it's such a simple entity. Unlike you, vastly complex, developed entity, spanning multiple orders of magnitude in computational complexity. So it's like a water balloon.
It is, but it is subject to quantization that is, in a lot of ways, unintuitive, because we don't really have any basis to relate to quantization, because everything we can directly experience is continuous.
Right. No,
like it would be basically the same thing as like the sun disappearing and then reappearing, 13 degrees further in the sky. If we actually experience life on the quantum scale, that's what it would actually be like.
This is sounding very fancy. Continue.
Well, it's important to bring these things up because that's the microscale limit of causality. We're still part of causality. What we are builds off the microscale limit, but the energy starts to collapse the maximum state, which gives the appearance of solids, but it's just the appearance of a solid. So we have to be very careful. Like I was watching, not to get too off topic, but I was watching a conversation about panpsychism yesterday with some philosophers, and they were saying, well, we're absolutely certain that consciousness comes from the brain. And I said, why? What you can be certain about is that it feels like consciousness comes from the brain. That's what you could be certain about. You could be certain that brain has something to do with consciousness, because without a brain, we can't be conscious. But is that even true? Because there was a guy born without a large segment of his brain who is still largely functional. So we cannot jump to that conclusion. But these conclusions, these axioms are appealing, but we have to resist them, because if we choose the wrong axiom, we will invariably get errors in our assumptions.
We could get a two-dimensional sun.
Well, you're eventually going to get something that is not consistent with reality. Your axioms can't contradict reality, because if they do, you're basically setting up a wall upon which a force is going to manifest, which is going to eventually break that wall. But if the wall is part of your architecture of axioms, it's unbreakable because you're imposing it. So you've got basically a immovable movable object, unstoppable force situation, which leads to a plethora of divergent results, i.e. more complexity, less clarity over time that you see in systems like the Standard Model. It's literally getting harder to understand that over time.
I think we may have just broken H8 Knight. It's good to see you. It's good to see you, my man there. Dude, I still want to do a collab with you, just talking about like some, I don't know, like just either just standard, just takes on either like the news, politics, because I like your perspective, I like your passion, and I think we're kind of scaring him. But if there's one thing I know from an immovable force, and strike that, reverse it, unstoppable force, immovable object, you got to grind out of Terek Valley in World of Warcraft to be able to have access to those things, because they are useful things, or at least at that point in the meta there. But what I'm taking away is, and again, a little bit off topic, but if there are additional dimensions that we don't normally kind of observe, and if these are just happen to be specific fields or forms of energy or something like that, once you start getting on the quantum level, it sounds like we kind of start effing around with them. All of a sudden, we're getting hints of maybe some dimensional energy transfer, or we're seeing different things, because all of a sudden it's like, whoa, oh, you have a muon. Oh, it's the opposite of an electron. But it's also like 125 times more mass than the proton. It's like, Nani, what the heck is going on here? I mean, could that be related to, I don't know, maybe we're tickling the space-time continuing. It's kind of going to tickle me Elmo and giving us additional energy, and thereby the price is raising, and we're observing other things. I just vomited a lot of words out there to try to relate a whole lot of things. Continue on with your explanation.
Well, that was about it. We could go into a derivation of the model.
Pinoid, you might actually be right there. Sorry.
We could go into a story about, because it seems like some of your audience members are a little discouraged. So I don't want to turn your audience off.
How about this? We started with the history. We got to the Copenhagen interpretation and everything. So, like, how did we get here? Like, could you give us a little bit of what a lot of the mainstream physics community and maybe some of the history is, and where you think maybe they got a little bit off track and maybe just need to kind of be reeled into maybe some core fundamentals? I realize I asked like
they went off track before Pythagoras.
Oh.
So
elaborate.
I can't even tell you at what point the axioms would have been okay, because Pythagoras' approach, it did have problems. And Plato sort of solidified those problems and going in a really unscientific direction by equating geometry to elementals. Which is, I mean, I've never heard of anybody doing anything like this. And it
that was the basis for Thad Roberts' geometry.
Well, what is it that's a turnoff? What is it that's a turnoff about astrology?
Oh.
What's the, like, why is that cringe? Because it's not
I
really
personally
precise.
don't. It gets said that it's not scientific.
Exactly.
People say.
Exactly. So you get this sort of whiff of unscientificality, right? You're just like, what the hell do you mean air has, whatever shape associated with it? That's completely unintuitive. Air doesn't really seem to have a shape without its container. The gas expands to the volume of the container that it occupies. the volume is undefined for a gas, but for its imposed boundary. Right?
So it is kind of like a waterbed. It's like, oh, you got a bed, you perturb it in one spot, something else happens somewhere, and it's
Well, not in the case of a
I would
gas. Not in the case of a gas. That a gas will just expand to fill its container. A liquid will conform because a liquid has a fixed volume, but not a fixed shape, whereas a gas has neither fixed volume nor shape. So it's, I think, to anybody who's really thought about this stuff a lot, Plato's approach was not. It wouldn't have felt like it was going in the right direction to get a deeper understanding of material causality, because the direction they ended up going in was the Mendelevian periodic table, a materialist numerical analysis of maximally objective observables, things like solubility, reactivity,
Right.
very
I mean,
strategic,
it got us
repeatable
through a lot
things.
of it got us through a lot of history. I mean, that whole, or at least maybe not so much in the Platonic forms. And again, I mean, only so
Because
many instruments at
it's
the
extremely
time.
complicated. It's extremely
Right.
complicated because you're making it seem like there's a mistake that was just led to horrible. Well, I'm not saying you're making it seem like that, but it's easy to fall into, a simple dichotomous thinking where it's like, what are you saying? Everything's wrong? It's like, no, not everything's wrong. And certain things were amazing. Like calculus is amazing. A lot of numerical methods were amazing. The level of precision that was achieved with regards to the abstract precision of measurements was unprecedented, and that was awesome. But that's not the full picture. So the way I would encourage people to look at it is that there have been amazing contributions, and ultimately, without going back to before Pythagoras, we never could have got to the right answer, because we have to argue for every axiom. Every axiom has to be defended. You can't just plop an axiom out of nowhere and expect that to be enough.
That's I can't actually disagree with that. And occasionally, I think this is what makes a lot of folks within many communities terrified, because it's like, well, these are our axioms, these are our truths. How do we know they're true? Well, everyone says they're true. It's like, well, who said it first? Well, this person. Did they have all the resources we have nowadays? No. Why do we still think this is true?
If you want to
This
see,
is what
like,
arguments are based off of. If the basis of all arguments aren't true, then we got to go back and redo all our work, and that sounds like a lot of work.
we'll have a look at what is it, the proof of God? One of these yahoos in the medieval times could put forward a proof of God, right? Basically comes back to, well, something exists, therefore it was caused, because anything that exists was caused. And if it was caused, it has a beginning, and if it has a beginning, it has an end. So the beginner, the thing which instantiated the beginning, is God. Some type of thing. So it's basically, you can see
I
that
listened to one of those the other day. It was missing
could
the
see
mark.
that
I
it's
like Christopher. He did a pretty decent job. Was it what I remember is he had at one point, sorry to cut you off, Jed, but basically like a type or time B or something like that, where it's like, all right, if you have a system, and kind of like the whole, like with Dr. Weinstein's geometric unity, it's like, if you have an observerse, doesn't that naturally lead to the question of who went click? I don't know. I don't know. Have the
absolutely.
answer.
And I mean that argument itself has not been defeated by anyone, but it's shit, right? Because it is completely baseless to assume that everything that exists was caused. Just because the things that exist are subject to causality doesn't mean that what exists was caused. That's a false
Whoa.
equivalence.
What if it just was?
Precisely, and this is what everyone believed until the instantiation of Christianity. So if you're going to posit a created universe, you're on the side of people who oppress science quite a bit for quite a while.
Now we're just talking the straight up reality, like interpretation right here.
That's what physics is. That's what physics is. It all ties together because it's all about the ultimate questions of where do we come from, where are we going. There's really only about 10 linearly independent questions in the entirety of material causality.
Right. And obviously the answer is Cotton and Joe. I'm sorry. You
I
said
thought it
where
was
did we come
40.
from? Where did we
I thought it
go?
was 42. I thought it was 42.
Well, the funny thing is, according to the number of intricacies, it comes up to 44, and then I think he like subtracts off 2 or anything. All I know is my interpretation. I see the number 44, and if that's a total of like potential hinges or something like that from reality itself, if you subtract 2 dimensions of space, you come back down to 42. That's what leads me to think that the vortex thing might be right. I don't know.
So maybe lop off the extrema because they're undefined.
I don't
It's
care.
just a suggestion. It's just a suggestion
It's
because
very
if that theory is correct, it is, monumental discovery. So kudos to the guy who put that work together. I haven't had a chance to validate it, even if it's wrong. Good effort, but if it's right,
he said just
big
go
discovery.
to Wolfram. He just said go to Wolfram and just plug in these things. And I'm like, the 2 things that give me hope for Mr. Roberts there is the sheer fact that number 1, I listened to that video, and 12 hours later, basically they had that muon thing where it calculated it further. I'm like, I forget whether you went over this in the video or not. Does this help your argument? He's like, totally. And then I looked at the numbers. I looked at the projected numbers that they had. They got to in an even higher level of digits. And I looked at his prediction, and I'm like, he's got basically their numbers within the error bars, and it keeps calculating there. And he has this for all 17 elementary particles, and he's using like established mathematics and physics and everything. That in his TED Talk that has like 1.5 million views from 10 years ago, it actually was flagged by saying it's like, these speakers' views are his views alone and do not represent the physics community. So the sheer fact that he was basically given a warning, at least on the internet, makes me think maybe he has something. But
there's been a massive aversion to panpsychic / monad type models since Christianity, basically, and probably even before.
you don't want to question God.
Well, it instantiates
unless you're a Hebrew.
It instantiates the impersonal God, which proves that other gods aren't as real as that one. So there's a lot of people that want to have a monopoly on theology because of all the money it brings and power and control, right? So that is basically controlling the destiny of Europe to such an extent that it does warrant mentioning, because otherwise these discoveries don't make a lot of sense.
Are you saying for power? Sorry to cut you off, but are you saying for the purpose of power, money, and prestige, people might not necessarily be telling us the whole truth? How dare somebody?
I know, it's a good thing you're sitting down for that level of a shocking revelation.
Oh, I'm going to need something more than that.
Did you want to get a drink?
Oh, I have.
It's always hard to deal with these cataclysmic revelations. I know. We've all been there. But yeah, like where'd the Big Bang come from, right? It was a priest that came up with it. And it's like the Big Bang could easily be disproven. Easily. But for some reason it's still believed.
Did you just challenge the Big Bang? Jen, how dare you?
It violates, it itself violates causality because it's admitted singularity, which violates causality. You're saying, well, we're going to suspend causality here because reasons. It's like, no, you don't get to do that. Just because the universe, you think you've observed that the universe is expanding now, doesn't mean you can infer that it was in a state of infinite density at some point in the past. You don't even know if that question makes sense because, again, you're asserting a beginning to the universe. Where do you make this assertion? What evidence do you have to support that what we see at night when we look up, that vast expanse, had a beginning?
All I know is I looked at a picture of the CMB on, what was it? Not Exploring the Universe, but Event Horizon's channel. He had on Professor Keating. And on the little photo for the thumbnail that they had of that video, I look at it and they talk about, what about that cold spot in the CMB? And I look at that. And then and again, I am totally biased of this because I have my pre-existing Bayesian priors. And when I took geometry, there was one shape that stuck in my head. And god dang, it looked a heck of a lot like that hyperbolic figure 8 knot. And I'm looking at that bare spot and I'm like, this is creepy. And again, it's probably just my Bayesian priors there, but it kind of looked like
I can tell you how that works.
Okay, how did we get the spare spot in this universe? Hold on, I'll bring it up.
I will pull up my blog so that it's a bit easier to follow along, because I actually do talk about that at some point. Let's see here. It's on the nature of space. So that's Church of Entropy on WordPress, and you could check that out. My latest article, I really like it. Let's see here. Okay, nature of space. And look here. Okay. So you're wondering why this shape is a thing, right?
Wait, hold on. Is this new? Did you just put this out?
A little while ago.
Okay, because I was gonna say, is like you had that monad stuff, and all of a sudden I'm like, wait, you just did this?
No, this was in, let's see, June 2020.
Okay.
All right, so why is there a non-zero temperature in the void?
CMB.
Why is there CMB?
Because
Big Bang? Just kidding.
well, I mean that's the thought. It's like
you don't
certain
know.
bit of this light maybe crystallized after
I'm
the
going to
Big
tell you
Bang.
though. I'm going to tell you why. I'm going to derive it with you right now using thermo. Okay. So what is absolute zero?
Negative 271 Kelvin, 72.
No, I'm talking about theoretically. What is it?
Oh yeah, there's no motion. There's essentially no entropy.
Absolute cessation of any motion, right?
Right.
Can we observe such a system?
We get close.
And what happens if we try to observe it? Quantum mechanically, what happens? We interfere with it, yes?
Right.
And therefore we disturb it from its state. So even if this state exists, we can't observe it because our very act of observing it would deviate it from that state, i.e. put it into a higher state. Because remember, what's observation? Interference. What does interference do? If something's in the universal lowest energy state, interference can only shove it in one direction. It can't go down, can it? Not if it's at the bottom, right? You can't get more solid. Like there's no such thing as slower than cessation, is there?
It's well, I mean, there's apparently from nothing there is nothing.
Because we're talking about vibrational. We're talking about vibrational motion, right? We can go if we're talking about velocity, we can define a negative velocity because that's just a vector distance. So if I could just start walking backwards, right? But when we're talking about vibrational motion, once the vibration stops, you can't get any slower than stopped, can you?
Jen, are you saying 0 divided by 0 equals 0?
That's not what I'm saying at all.
I still want to meme that into existence. I just say
no,
that.
It's undefined. It's undefined. You can't divide by 0.
No, I totally stole that from one of the Wolfram physics streams because at one point within something they were working on, it's like, well, we get 0 divided by 0 equals 0. And all of a sudden Steven's like, well, that's crazy. And but I sit there and I'm like, number one, it was hilarious. Number two, I'm sitting there and I'm like, they do an edit to the code. It's like, well, just remove that one parameter. I'm like, what if that parameter was actually right? I mean, how crazy would that be if for some reason the error you're getting that you need to account for that one thing was actually true? I don't know. I find it funny. Continue.
Well, I'm getting to the point of the CMB, right? So what happens if we try to observe absolute zero? Now, it deviates from absolute zero. It goes to a higher energy state than absolute zero because no lower energy state exists because it is impossible to define negative vibration. Do you agree with this?
Is it impossible if you use like I as an imaginary number?
But it's the thing. It's still vibration. That's the thing. It's still energy. That's my point. Is that there's no such thing as negative.
Wouldn't there be Wouldn't it be absorption? It's like the concept of vibranium.
No.
Neutralizes
absorption, excuse me. Absorption happens anytime there's a differential. That's a thermodynamic law. So if there's a difference in the heat energy of two systems in their contact, entropy says that they'll equalize that differential to 0. So that is happening above absolute zero. We're not talking about flux of heat. We're talking about literally slowing a vibrating system down to its absolute slowest vibration and down to no vibration by removing all the energy.
Well,
We can't go to negative. We can't remove, because what would it look like? I mean, if it's vibrating a little bit, it's got a little bit of energy. If it's vibrating a lot, it's got a lot of energy. If it's stopped, it's got no energy. It's at absolute zero. There's nothing below that energy-wise.
Now, I thought if you tried pulling on quarks and you pulled hard enough, you just get more quarks.
I don't acknowledge the existence of anything other than photons, protons, electrons, and neutrons. All these other things are hallucinations that have been made to look like they exist because of the measurement devices. This is why you can only get them on these super high energy devices, because it's literally a device effect, not a material under observation effect.
Holy crap.
That's why they have such a short lifetime. It's
Holy
like, oh my
crap.
God, it's a millionth of a second long. It's like, yeah, it doesn't exist, dummy. It's just an energetic signature because you perturb the system to such a high degree of internal energy that you saw eigenstates you never saw before. Ooh, they're still derived from the same material substance. Sorry. But I mean, that's a dead end. That's not going to go anywhere because you're just going to keep finding more particles. Like my theory predicts that standard model will just keep finding more particles. There's more anecdotal evidence in support of that because they just quote unquote, got more quote unquote, whatever evidence for a new particle. It's like, you're just going to keep discovering more. Every time you breach a new energetic level, you're going to discover more quote unquote particles because that's what you've axiomatized you're going to find. If you axiomatize differently, they're just different eigenstates.
What you just said there, and just with some of the research we've kind of just like at least causally gone over recently. The funny thing is, when you say that again, my Bayesian reaction is, well, that can't be true. And then I flip my mind onto, well, what if it was true? And if that's an observable effect, I do remember, what was it? Somebody on Discord the other day was showing me their essentially enhanced view of essentially what they believe to be, I believe, like a proton was actually. And basically they were showing me the actual pictures and their rendered view of basically the quarks, and their quarks weren't necessarily just the little ball things. It was kind of like the size thing and everything. And the funny thing is, I'm like, oh, well, it also has kind of like 3 primary loops, a hyperbolic figure 8 knot. Again, I have no idea. I find it interesting. Oh, and you have a new fan.
It's beyond interesting.
She has a YouTube channel. It's the Church of Entropy here on the YouTube. So I'll throw it in the chat. Continue explaining, Jen.
Yeah, if you want to bring on these people either today or some other time for me to talk to them, I'm more than happy to do that.
All right, well, let's make this more exciting. Let's throw the link in the chat.
Just to be clear, to introduce myself, because I don't know how I don't really think you know very much about me, Memes, but I was a tutor in math and other subjects starting from around grade 10, and I've just continued to do it and continue to develop my teaching abilities. And when I was working for the Royal Canadian Mounted Police as an audio video analyst, I got a chance to learn a lot of interesting stuff and teach it too. So I have this background in signal processing, physics, but also I've been teaching for a really long time. So these things that come up in the conceptual process, I'm familiar with them. I'm not going to be put off by a question that is quote unquote a dumb question, because to me, there's almost no dumb questions. There's bad faith questions, but that's, a minority of questions, right? So oftentimes when somebody tries to dismiss you because what your question is just too obvious, it's because they don't know how to answer it. Because the obvious things are actually really hard to explain. Example, time. What the heck is time? So freaking obvious. I mean, it's so freaking obvious what time is, right? I fucking forget it, man. I already need to define this shit, but you actually put someone on the spot to define time. It's going to be a garbage definition, isn't it? Because we just don't think about things that are quote unquote self-evident, do we? We take them for granted, aka subconsciously axiomatize them. So we got 2 types of axioms. We've got the axioms where we're not consciously aware of them, but they're acting. And the ones that we are consciously aware of, where we're hoping to impose them because we've convinced ourselves science axioms are tight, right? They're really good. We're going to use them. So the process is about reconciling those two things.
Are you
So
saying
I kind of got off the subject
people
here.
want to say things are true because they're true, and they just want them to be true, and they're just trying to meme it into existence?
So, some stuff feels true because it has to feel true, because if it didn't feel true, we would have died out evolutionarily a really long time ago.
Well, maybe that's a good
That's
thing.
all I'm saying. That's all I'm saying. Like, if getting your leg sawed off felt orgasmic, how long do you think that species would live?
Well, I mean, some folks. I mean, maybe that's kind of their thing and everything. On
But you
large
understand the argument,
scale,
right?
right. And I apologize for what I'm about to do right here, just because I'm sorry. It's too good. I apologize for my. Hold on. No. I did the wrong thing. I apologize for my racism right here, because it just brings me back to a happier time. Here we go.
Our country reeks of trees. Our yaks are really large, and they smell like rotting beef carcasses. And we have to clean up after them, and our saddle sores are the best. We proudly wear women's clothing, and searing sand blows up our skirts. And the buzzards, they soar overhead, and poisonous snakes will devour us whole, and our bones will bleach in the sun.
That's it.
And we will probably go to and that is our great reward for being the royal Canadian kilted Yaxman.
All right, that's good enough. I think my point was communicated. Again, I apologize for my internationalism. It was just ingrained in me from childhood, like that, just like that, and like the log song itself. It's like
some people are like slinkies. It's fun to push them down the stairs and watch them fall.
See, well, either that or log. It's like do 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 do. What rolls downstairs over and bears rolls over your neighbor's dog. What's great for a snack and fits on your back? It's log, log, log. I'm sorry, it's part of my childhood. It's ingrained in me. I blame the dang microtubules. You were explaining the CMB.
Okay, so I'm okay. I understand. You're a based skeptic, and you don't want to necessarily agree with everything I'm saying. But maybe just for the sake of the argument, to understand what the actual argument is.
I'm totally willing to. Well, I'm a skeptic. It's like I got to be willing to entertain an idea. I don't need to belabor the point. Continue. Nothing is nothing.
So the point I was getting to is that if we attempt to observe a system which exists at absolute zero, our very act of observing it will perturb it from the state of absolute zero. And since this is the lowest state of energy corresponding to temperature, there might be another absolute, energy corresponding to just purely mass, right? But if we're just looking at thermal energy, this is the bottom of the ladder, right? Bottom of the proverbial energy ladder of heat-related things is absolute zero, just by definition.
Right. There is no moment. Basically, you can no longer have any entropy because nothing's going on.
Well, you can have entropy depending on how you define it, because entropy has to do with geometry, and we can get into that later. But let's just look at it from a strictly.
All right.
Let's just look at it from it's an important thing, but it would take hours to go into. But let's just look at it from that perspective of purely heat energy and say, okay, it's at the bottom. Let's say hypothetically it exists, and let's say we're going to go and observe it. And if we want to do that, we're going to shoot ourselves in the foot, because the very act of observing it's going to involve interfering with it by the interpretation of Copenhagen, which is going to perturb it from this state. And because it's already at the lowest state, the only place for it to go is a higher state, which is no longer absolute zero, is it? So we have this problem, theoretically, with the observation of an absolute zero system. But we also have this thing that we can deduce. If we look at the universe and say, okay, energy dissipates, entropy increases, Therefore, statistically speaking, the majority, the largest, if you divide up matter into all of its subsequent constituent categories, the largest category should be the maximum entropy or minimum energy state. Because it's like a mountain. The base is the biggest. Then it gets smaller as you go up, because that's just how energy works. You got a maximum in the lowest energy state, but you still have mass in higher energy states. Like a mountain is not flat, right? So there is population in higher energy the metaphor for energy here being height. There is population in higher energy states. It's just less. So the universe,
there's a distribution of mass or something.
Precisely. And the mountain is actually an excellent metaphor for it. So we can deduce that, like, from what we can tell, everything should be careening towards absolute zero. Because that's what entropy says is going to happen. Entropy says everything's just effing off. All the heat's going away. All the orders, blah, 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 to nothingness. Everything is just crashing towards absolute zero. But then when we get there, what happens? Observation brings the energy up. Observation isn't something just people do. Quantum mechanically, observation is any interference. Anytime there's interference in the universe itself, you're creating non-absolute zero states. There's where your CMB is coming from. The very act of the universe pulling itself together through gravity is computationally equivalent. So the example that I use is of us trying to measure the absolute zero state. We're not in this picture anymore. It's the universe observing itself. Because what is observation? It's interference. What does gravity do? Pulls things together, aka causes them to interfere. So you're going to have a base level energy, which you're going to have a non-zero base level universal energy corresponding to this self-interfering effect, which deviates the system from absolute zero via observation. Thank you for paying attention, and welcome to the show. Thank you so much for joining. It's always great to meet new people, especially people who are interested in these big questions and have spent time really grappling with them, because it's just to me, it's just a great pastime.
Right. I don't know about everyone else, but my mind just got blown, so I need to wind down for a few seconds.
Yeah.
Gotta get the squirrel. So welcome, LDG.
Love it.
How we doing, brother?
What's going on, everybody? How you doing? Hello, Church of Entropy.
Hey, you could just call me Jen. But yeah, Church is fine, or whatever you're most
That's funny.
with.
That's my initials. Geeks Enjoy Nerdotica. Jen. There we go. That's easy to remember.
Ooh.
Yeah, it's the most common name for a female in the year 1980. So I'm in that nice meaty part of the curve.
Holy crap. I'm not going to talk about Xmas. Continue. No, just points, this, that, relatability. So, yes, LDG himself has been working on some certain things within more of the computer side of things. So, what are you taking away from this, LDG? Is any of this making sense? Is any of this sticking? Or are we going with the Waterworld universe?
No. I always enjoy a good a nerd discussion about things like this, especially physics and the universe and whatnot. And from what I heard, I just came in because, again, thank you, YouTube, for not giving me the notification that memes went live. But I do my diligence and found you. So I kind of came in late into the conversation. But basically, if I get this correct, were you basically stating that there is no such thing as absolute zero, depending on the state of reference and the scope of the unit of measurement?
What I'm saying is that it exists as a theoretical state, but is unobservable by virtue of interference effects of observation.
Gotcha. It can only exist theoretically.
But it has
Basically.
existence. But it has an existence. And it's the same with the sphere. And that's something we haven't really got to yet, is how the sphere is central to the theory, is that a perfect sphere is conceivable, but it is not observable. Because if I charge you with the job to find me a perfect sphere and prove to me that it's perfect, you're going to have to measure it at some point. So even if it was perfect to begin with, the very act of you measuring it screws it up. So I've sent you on a wild goose chase, but the sphere still obviously has a tangible, real existence. It's just unobservable.
Gotcha. Kind of like pi. Pi exists, but the second you look at it, it changes slightly.
I know. As soon as I see pi, I just put it in my mouth.
It does. It's not looking at it that changes pi. It's to observe. But you could say that to observe a perfect sphere is the same as finding the last digit in pi.
Yes,
Not possible.
exactly. You can't do that, but the second you try to, the number changes.
But
The
you
only way
can
to get-
conceive of it. You could conceive of it
You
because
can
all you have to
conceive of
do
it,
is say,
yes.
well, what's pi? It's the ratio between the perimeter
The
and
circumference and the
diameter of a circle,
diameter.
right?
Yep.
That's all it is. And you can sum it up
Absolutely.
in a sentence, but you can't then go to the end of that numerical approximation. So it's very important to distinguish between abstractions, ideal abstractions, and what is real, what is actually possible to observe in the reality, because this abstract
Gotcha.
realm, aka the Platonic monad, it does dictate the material reality, but there's a change that happens. Like the Platonic realm is where the perfect sphere exists, and our realm is where the perfect sphere clearly affects the shapes of things. Look at your head, look at your eyes, right? Look at everything. Look at a bubble,
Mhm.
blow a bubble. The bubble wants to be a sphere, but it can't
Mhm.
ever be perfect sphere. Why? Because we're living in the quote concrete realm of imperfection, right? That's why Plato compared the ideal realm, the perfect shapes, with this realm that has these sort of cheap imitation perfect shapes that they can really try, but they're never going to quite nail the mark.
Gotcha.
So we're a
Because
whole
even
bunch
a
of
black
shadow
hole isn't a
clones.
perfect sphere.
How dare you?
We're not entirely sure what that is. So for constructs like a black hole, we have to build those up from just logic. So we say, well, we've got this thing called gravity. Let's find out how gravity behaves at the extrema. So what happens when there's almost no gravity versus when there's almost infinity gravity? Does it even make sense to
Mhm.
talk about infinity gravity? Can we define a region where the gravity is infinite? And the answer is no, because we have something called the Pauli exclusion principle. So the logic is mass creates gravity, gravity causes attraction, attraction eventually imposes the limits of the Pauli exclusion principle. Do you know what that is?
You can't have two fermions, or basically things that are technically have mass, in the same point of space at the same
Quantum
time.
state. Quantum state. We want to be careful to use the correct nomenclature here, because space is not defined at the prime order of causality. The prime order of causality defines matter, aka mass, aka space-time. To get to time, we're taking a step of imposition of our axiom. So you got to be super careful. This is where all the mistakes in
uh,
physics come from.
This fascinates me, because the first thing Professor Keating ever asked me when I wanted to see more of, I'm like, could you explain like strange stars or something like that? Because I'd watched the Kurtzevig in a nutshell video on that. It's like, what are these things? It's like, well, they might be strange quarks. I'm like, what is a strange quark? And apparently, one of the things that is at least theorized about strange quarks is they ignore the Pauli exclusion principle. And one of the things that I took away from listening to that 2-hour thing that Mr. Roberts put out was apparently a strange quark is the one thing that we don't really know all that well. And to me, I'm like, wait a second, is this the portal? I don't know, but continue.
Well, I have a hard time with that, because the Pauli exclusion principle is just the bound case of the Heisenberg uncertainty principle. They're the same principle. So what's Heisenberg saying? It's saying, well, if you go through a tiny little thing, you're going to get shoved into one of your proper eigenstates. And Pauli exclusion principle is saying is if you're shoved into a discrete region, right, then no two fermions can occupy identical regions, aka quantum states. So these two things are, one is the curled up version of the other. I don't know if that makes sense, but I would be very suspicious if someone was saying that the Pauli exclusion principle could be violated, because we have basically nothing but evidence for the Pauli exclusion principle being true. So if you wanted to understand what black holes or dark matter were from the point of view of my system, I've got a video here showing a time-lapse drawing of just your basic mechanism for how a novel star is excluded from a hyperdense region. What's a hyperdense region? Well, we think about the universe as a whole, and like I said earlier, we go to the maxima. Hyperdense region is where the gravity is at a maximum, but we know it can't go to infinity because that would violate the Pauli exclusion principle. mean, these are literal entities, right? Like, how many Cheerios can you fit in a Cheerio box? Like, there's a finite number of Cheerios. Why? Because literally that
You can't
box
have
has a finite size.
you can't have two Cheerios in the same spot.
And it really does work like that. And for people who want to argue against that, I'll just say, like, that this is what chemistry is based on. You can't have three electrons in the s orbital. Like that's the reason is because of the Pauli exclusion principle. So to deny that would be basically, I mean, it calls chemistry into question, doesn't it?
Well, aren't we calling everything into question? Well, actually, that's very interesting right there, because is that why we kind of technically think of, like, I don't know, like an electron as like a particle, even though it's like, well, it's kind of electromagnetic wave function or something here. Although, actually, is that what a muon is? Is that why it has so much more mass and stuff? What if they shoved a whole bunch more, like, wait, no, different particles. Sorry, I fail. Continue.
낮에는 따사로운 인간적인 여자 커피 한 잔에 여유를 아는 품격 있는 여자.
So we're basically going to use a thought experiment to say, okay, I'm interested right now in regions of the universe where I'm bumping up against this quantum limit, maximum density regions. And what do I know about these regions? Well, gravity's the dominating force, which means that the other things that could impact the system, like electricity, are not active. Gravity's dominating. Because to get enough gravity that gravity's got to dominate if you're in the most dense region of the universe, right? But we also know that there's a limit to how dense it can be. So we've got an unstoppable force immovable object thing, right? We have matter that wants to attract itself because of gravity, but we also have a limit to how much it can do that. And so if we just have this huge collapse of super dense matter, eventually a Cheerio is going to fall out of the box. And what's going to happen is that it's going to move not adjacent to that region. It's going to move sufficiently far away as to solve the problem of quantum state crowding, because this is literal universal law. The quantum states shall not be crowded. You don't get a vote as to whether you can crowd the quantum states. The universe doesn't. We don't. We can't. There's no way to get off that ramp. So we have a situation where gravity is essentially competing with the Pauli uncertainty principle. And once you get enough once you get a little extra mass that is contributing to that local center of mass, you have an ejection of matter to the boundary sufficiently far that it solves the problem of quantum state crowding, because you got to realize that the particles, the waveforms comprising this hyperdense region, are indistinguishable. Why? Because that's what entropy predicts. Indistinguishable particles, if they were distinguishable, there would be an energetic difference between them. The energetic difference would able to be transitioned, and it would just transition to whatever state had a higher gravity, right? So we don't get a lot of variation within the nature of these constituent waveforms. So to just move the hyperdense region, so you got sort of like a crystal coalescing in the center, if it just moves somewhere else within the region of this hyperdense matter, it doesn't solve the problem of quantum state crowding, it just moves it somewhere else, but it's still crowded. So it has to eject it to the boundary where it's no longer causing the possibility for the quantum states to be crowded. So this is your quantum state transition. This is what is going to create a new star. And what I've got here is the shape of this creation. So we have this quantization. Every time you reach the density maximum, out pops a star. And there's evidence for this type of mechanism operating at the center of our own galaxy. And then you've got the red. So the red line is the true path of the matter. And the green line is the pure form path. So that's the like an energetic geodesic from the perspective of God. But on the actual material level, what happened was a quantization of ejections happening that you could draw this perfect spiral through, but what actually physically happened was more of a stair stepping, which is why you have two different paths. So essentially your red path is dictated by your green path, which is your pure form path, which is unobservable, and what's observable is the red path.
So
to see
we're
how
talking
there's
about
this
spirals in Plato's cave.
We're
It's-
talking
it's-
about
it's-
how the constructs in the cave dictate what we can observe
Yeah.
directly. Sorry, go ahead.
No. So if I get this correctly, this is no different than, I'm sorry, changing a waveform from analog to digital. You get the quantization where it should be this, but because of reasons, it becomes quantized, and we actually observe a different, similar but different shape when it actually happens.
Real reality, i.e. the reality we're occupying right now, the material realm, is quantized.
Yeah.
Ideal reality, which dictates the progression of real reality, is continuous. That's why the green is nice and smooth, and the red is. So I guess you're saying that the green is an analog signal, and the red is
Yes.
digital. Oh, nice one. Yeah. See, I
Yes.
love these metaphors.
Yes.
That's a great metaphor.
That's how I speak,
gravity?
actually.
No. LGG is quite good at that. I know he's working on some interesting projects as well. Hashtag Project Prometheus.
Prometheus.
But is gravity just gravity? Like, from what I'm taking from this, it's like, all right, you got so much stuff, it's quantized, but what if gravity is just gravity as we know it?
Mass is quantized, gravity isn't.
Oh,
Mass is observable, gravity is not directly observable.
so we're just trying to plug the wrong plug into the outlet.
Yeah, you can summarize this conceptual issue really quickly by saying mass is quantized, gravity isn't.
Yes.
So we've been trying to
cannot equate the
overcomplicate
two.
this for a while.
We haven't defined it yet. We
Okay,
we know it exists. We're able to see its effects, but as far as quantifying gravity, we haven't done it yet. Now there are some
Isolating,
theories out there.
not quantifying. We can quantify it. We can't isolate it.
Okay.
We
That
cannot.
works.
Okay, think of it like this. Can I pour you a glass of gravity? No.
Yeah.
Can I pour you a glass of mass? Well, sure. Orange juice has mass. Glug glug glug.
Exactly.
There's your difference.
The one pop cultural counterpoint I might have is Mechagodzilla may disagree with you in the new Godzilla vs. Kong movie. Now, I'm not saying you could pour it, but you can punch a giant atomic lizard with it, apparently. The energy things, I think, are gravity-based there. That's why Godzilla didn't like it. They had the established technology in the movie, basically being able to actually, like, do anti-gravity stuff, and they had to reverse the gravity thrusters in the Hollow Earth. Minor spoilers, my bad.
Well, I mean, when we do get to the point, if we can ever isolate gravity, I think that would be a huge accomplishment and answer a lot of questions. Right
It's
now,
already
the
been
best-
it's already been explained. It just hasn't been well understood. Are you familiar with the de Broglie waves or the wave?
No.
The matter equation.
No, I'd have to look it up.
All matter has corresponding waveform and associated frequencies, including the maximum entropy state. So a solid admits one waveform, one frequency. It's just a matter of if you want, quote, anti-gravity, you just need to reverse that frequency. The trick is not destroying the system in doing that. That's why it's such a precise,
Do we know if
difficult science?
Question.
Because
does gravity emit like a field, or is it a omnispherical force or omnispherical? You know what I mean? Like a magnet. You know how magnets like give you like two fields. Does
the way I
gravity
understand it,
have they shown that gravity works the same way as a magnet field?
the way I understand it is that gravity operates instantly because matter is entangled. So the action of gravity appears to be instantaneous. So that means that you can define a field, but it's not the same kind of field as an electromagnetic field. That field has to do with this light speed. So that travels at a finite speed.
Now
whereas
wouldn't it
gravity
technically-
doesn't.
Right. Now, like, wouldn't gravity be kind of like omnidirectional? Because as far as
Yeah.
I know, like, even if like the Earth is spinning and stuff like that, yeah, conceptually you can have like the magnetic waves and stuff coming out. But if you're either at like magnetic north or magnetic south or something, it's like gravity should still affect you the same. Basically, if you have a spinning body, like the spin might affect the electric field, but the actual, like, it, depending on what point you were from that particular planet, moon, whatever it is, like, does that affect gravity?
Well,
The way to think-
the
the way
same
to
thing
think-
works with a magnet. Like it doesn't matter where you put the paper clip on a magnet; it's still going to attract to the magnet, just because it's north or south. I was having a conversation with this the other day with somebody, and they were trying to say that there was a difference between two magnets interacting with each other, and a magnetic, not a magnetic, but a metal being attracted to a magnet in any kind of pole. I mean, I think gravity could work the same way. It doesn't matter where you are, but is the force omni where every direction is in towards the center, or does it still also work as a field, but at the same time where the paperclip, and it doesn't matter where we are on the planet, we're still going to get stuck to it.
Could just be our observation as well.
And the only way to observe that is by taking two like say two black holes and putting them next to each other, because they both emit, but they both have gravity, obviously. And so I think that might be the only way for me to think how to observe if gravity is omnidirectional or in a field. And if I believe that would be an excellent answer to find out, because that would tell us a lot if gravity does act in like a cardioid kind of field, or is it omnidirectional?
Well,
that would be
waveforms are restricted to their proper eigenstates, which is where you get these derivative states that you're alluding to here. That's not precluded. Gravity so the way I look at it is you have indistinguishable waveforms in dark matter, and they're near absolute zero, but they can't reach it because every time they do, they bounce off it when another system observes them, and it lets off some very low energy radiation in the process. So you have a bunch of indistinguishable fermions in a kind of soup, and they have a single gravitational field, which may consist of which will have waveform effects, right? It's not just a flat single attracting dot, it's an oscillating thing. And you can see this in the renditions that they've done for two black holes oscillating around each other. Like it creates this enormous torsion due to the increase in the relative sizes of their orbitals from coming into decreased size of orbits from the increasing velocity from decreasing sized orbits from increased gravity. Jeez, this stuff is tough. Can you see how challenging it is? Just like
how dare you keep all these parameters of the universe itself in your head? If only we could write them down.
It's always got to be logically tight. Everything has to follow a strict causality, because the moment your causality breaks down, the moment you invoke something that you're not totally sure about, the whole thing just falls apart.
Right. And I mean, as human beings, it's like we I think we've done pretty decently well over thousands of years, like based upon what we have. But it's like, as we're saying, it's like, all right, so even if we were off just a little bit from our observations, it's like, if we tighten this stuff up just a bit and actually show that this is true because of these reasons, and we're a hell of a lot more sure than some of the other things, it's like, how much far could we get? How much could even just a small bit of error correction just down the causal chain lead to exponential results?
Think of it like this, okay? Think of it just building up from nothing. So we have to, in our minds, just clear our minds to nothing, just void. And then what we want to do is start to introduce mass into that void. Just throw in a couple of neutrons, just get out this salt shaker. And what happens to those neutrons? Well, they're going to be attracting each other, right? Because of gravity. And then what's that going to look like? Well, for a while, everything's just going to be very simply going to what shape?
A spiral. A spin.
Sphere.
Yeah, sphere.
It's sphere.
There you go.
It's spherical.
Okay, so just follow me here. So sphere is step one. So this is just very straightforward. Neutron sphere. Why is it a sphere? That's the shape that minimizes the torque about the center of the object. Maximally symmetric object. Got a sphere, okay? But how big can that sphere get before the Pauli exclusion principle starts to exclude matter from a gravity collapse in the center. Eventually, you're going to reach a point where you have so much matter in one region that the center of that region can't fit anymore in it, but it's the center of mass. And what's gravity want to do? It wants to attract matter towards the center of mass, but it can't fit. So
but there's a breaking point, isn't there?
It gets ejected to the perimeter. It gets ejected only far enough that it solves the problem of quantum state exclusion, because the universe is very frugal with energy. It's only going to do as much as it needs to maintain its own laws. It's not going to send it to the other end of the universe, right? Because that would be like, well, where did all that energy come from? No, it's just the internal energy of the gravity itself saying, well, no, there's a limit to how dense this is, and getting just eject it to the boundary. So what does that do? That's where your wave action's coming from. That's where the waveform action of these things is starting to come from. What does that do? Think about it. You get the collapse in the center. What does it do? And another sphere pops out at the periphery. But what does that sphere do? It then collapses towards the original gravitational center because it's still the local gravity well. What does that motion look like?
It looks kind of like a star, I think.
No, not that's what the shape looks like. I'm talking about the motion. Oh. What motion is resulting from that? They're going to start to spiral into each other. But then what's going to happen? You're going to get another gravity. You're going to get another gravity collapse as soon as you get to that maximum density. There's a limit to how big a star can be. Notice that how when stars are really effing big, they're really not dense at all. Why? Because there's a limit to density. And when you have mass in one area, all like the center of mass reference frame is literally what's happening with that gravity field, because it's acting as though it's acting in the pure form realm, because gravity's pure form is acting everywhere. So even though the star is super diffuse, all of its gravity is still acting as though it were in the geometric center, which is always giving the possibility to precipitate more quantum state exclusion. So you have this inverse relationship. With bigger a star is, the less dense it has to be, because it just can't have that much total mass, because that would cause it to
black hole
rip apart, basically.
Do things tend to spin in the same direction in the universe?
They minimize energy required. Okay, think about it like this, okay? Why does, when you put a bunch of clocks with the tick-tocks on them, and when you put those all in the same room, why do they synchronize their periods?
It's because of the oscillation.
Well, why? I mean, they're not touching each other because they are a waveform. Because waveforms are subject to entropy, and therefore the amount of work that these waveforms do on each other will be minimized over time, and the state which minimizes work these waveforms do on each other is synchronization. So you'll have a synchronization also in the dark matter. And what does that look like? It's them like, basically, it's kind of like the way Earth is with the moon, right? It's always facing us. It's sort of spiral, like going around and around, tracing out a sort of spiral.
I like it.
Going, like if they were going in the same direction, they'd have a net torque.
I'm actually kind of curious now. Let me look into this while you continue to explain.
Well, just think about it. If they're going in the same direction as the net torque, where's the net torque coming from? You got to find the max entropy min energy state. So the min energy state is the one that has net torque of 0. But each planet creates a torque, right? Because what is torque? R cross
Let's create
F, right?
Gravity, right?
Torque is R cross F. Cross product between the center. It's not the center of either body. It's the center of mass of the entire system, right? Like the moon doesn't orbit the Earth and the moon orbit their shared center of mass. It's the same in the dark matter. So what does that look like from an outside perspective? Is it more or less like a balanced spiraling sort of like the shape of the DNA?
Kind of like a Mandelbrot?
I would say it's more like a DNA. Like if you think of that shape sort of unfolding.
Nothing
It
wrong with
really
the double
depends
helix.
on it depends on the parameters of the mass itself, right? Like in the particular parameters of our planet, this is the type of spiral motion that you get. I've got it on the screen right now, right? But because the sun is so big, it appears to be solid. It appears to be not moving, and all the planets are simping for it, right? It's got a gaggle of fans following around. But if it was the sun and another sun-sized thing, it would be those two things going around each other, aka going around their
It
shared
depends how
center
you
of
look
mass.
at it, I guess. Yeah, looking at it from the side, I agree with you. But looking at it like head on would be more like an infinite.
It's
Depends upon
extremely
the
hard to
observer.
visualize.
Spiral.
It's extremely hard to visualize these things. That's why most of the time what you're doing is
That's why I
strategically
love the Mandelbrot.
you're projecting into a lower dimension. So it's almost impossible to visualize it as it actually is, because the causality is 3 + 1 dimensional, and it's 3 + 1, not 4, because the 1 is entangled with the 3. So it becomes a bit challenging to visualize such a complex object. But so we don't need to visualize it. We can just look at all the different projections and then contemplate them separately together, and then sort of work towards a unified understanding.
So, quick question about the when you were talking about the Cheerios and black holes. Before when you were talking about the molecules getting to a point where they have to come out the box. Okay, so if you have a bowl of Cheerios, if you have a box of Cheerios and you try stuffing it with Cheerios, and you get to the point of you can't fit any more Cheerios in, right? And you put one more Cheerio in. What happens if a Cheerio can escape? What's the other option of happening? What's the other?
Why wouldn't it be able to
endpoint?
escape?
Just theoretically, what's the next possible thing that would
you have the
happen?
same volume, and it would undergo a phase change.
Nah, wait. No. Okay. I see how that could be.
It would become.
Mistaken.
I'm viewing it as at least
I
one
see where
Cheerio
you're-
would end up
okay.
being crushed or something.
What I'm trying to say is, yeah, exactly.
what
One
we have to
Cheerio would be
realize-
crushed. That you have
The
that
Cheerio
where
is a metaphor. The Cheerio exists in what appears to be a continuous causality. If you want to move a Cheerio across the table, it has to go through every intermediary position in the middle, right? When we're talking about the quantum reality, it's quantized. We don't experience quantized.
Just like there's space in between an atom, there's space in between a Cheerio.
Exactly.
So
the space is created. This space is created. That's the crazy part. This is one of the most important things. The space is literally created.
So that's what I'm thinking happens that I don't hear anybody talking about, is that, okay, so we take two, protons or photons, and we put them through a kaleidoscope, right? A collider. And the amount of force needed to hit these things smashes them to pieces. We literally break apart matter. We don't destroy it. It just changes shape, but we break apart matter, correct?
That would be a big discussion as to what's actually materially happening, because we'd need to go through and say, well, how are we defining the boundary between entities? Because the answer to that question depends on your own axiomatic framing thereof. I'm not trying to give you a hard time. I'm just saying this is an extremely important question, and I don't want to say something that is going to lead you in the wrong path.
No. Yeah, and this is all theoretical, but okay. So they have this where they take two particles, they collide against each other. They take a snapshot, and you see the subatomic particles spreading out. So we know that even an atom can be ripped apart, just like a Cheerio can be crushed, and the center circle can be completely. You can make a Cheerio smaller than what a Cheerio is just by crushing it itself, right? Isn't that what can happen? Isn't the black hole in the center of a black hole more than enough force?
No, it's bad. The Cheerios is just a metaphor. In my metaphor, these Cheerios are indestructible.
Well, so I'm saying
Cheerios
we know
can't
that
change. Like a neutron can't change. Like we have no evidence that these things could change.
Well, I don't know if they change, but breaking apart necessarily
I know.
changing. What I'm saying is that
you missed the quark part, I think. But continue.
I don't know. So in my analogy, a Cheerio is a particle. Okay, so black holes are made up of particles, mass.
But they're not, right? That's not actually what's going on. That's why it's just a metaphor. You can't take a metaphor and then use it to straw man what the position is, because the metaphor is just a metaphor. It's not actually what I'm saying. It's a way to make what I'm saying less challenging to understand by using an example that is intuitive.
Isn't it an eigenstate? It's a mimetic eigenstate.
Well, the eigenstates, there's different.
You're using it as an
eigenstates we can talk
example
about.
just to present something. No, I understand. You could use a different metaphor, but for this case, we were just happen to be using Cheerios.
Well, for this metaphor to work, the Cheerios would have to be indestructible, right? Like, this is the basis of it. Like, we're talking about what happens at the limit, the quantum limit. So we've already assumed that we've gone to the point that we're dealing with the base elements, the base waveforms, the base particles, if you want to call them that. But that's a misnomer, because a particle has a definition that's inconsistent with that. Particles have to exist in a 3 space. Particles have no volume, right? They're just a point, right? Like you can't just assume that points exist ad hoc, because we're not talking about a universe that has geometry. We're talking about causality that predicts geometry. Completely different approach. I'm not sure if that's clear.
I just want to say that, because an atom, okay, maybe I'm saying particles too loosely, but an atom can be broken down.
Call it a quantum.
We know that there's a lot of space between the nucleus and the...
Call it a quantum, because that's what it is. I mean, neutron is a quantum because it's the smallest indivisible entity, but let's say you can divide a neutron. Let's say you can destroy it. It's no longer a neutron. It's something else. It doesn't have neutron
until it
properties.
Forms back into a neutron.
What?
That's what I was saying. I was thinking like in a black hole where there's so much pressure is involved. Under that pressure, matter can take on a different state until it is ejected, and then once that pressure is gone, it reverts back thanks to
exactly
the universe.
And
it turns back into a neutron.
When it reverts,
for that moment, it isn't.
When it reverts, okay, it's instantiating causality, which means it's creating space and it's creating time. That's why we can measure how old things are, because the space around us was created at some point when we were excluded from the center of the sun, because that's where we come from. We're like shot out of the sun like a chicken lays an egg. Again, terrible metaphor.
Yeah, we're a sun fart. Yeah, I know. I mean,
the fart metaphor is creeping in again.
Or a sun burp.
Memes, can you smell it? Can you smell it?
She was explaining voltage and amperage via fart analogy to me. It totally worked.
Oh, the Duva got so triggered. That was classic. Oh, thank you so much, audience. I really appreciate, like, this is what I live for, because it's people like you and your audience that I've been working all this time to elucidate things for. And it's great to bring people in who have no experience in physics. But if you have even a bit of experience in physics, I've built this all up based on my own experiences teaching. So it's like, if I can give it to you in a simpler way, I will. I'm not trying to overcomplicate. I am doing my hardest to make this simple. It's just that this stuff, because it's so fundamental and is such a simple architecture, it's actually really hard to understand. So stuff can be simple and still be hard to understand because we're complex. We can relate more easily to complex things. That's why we prefer narratives, ultra complex things. And we can't remember data for shit without a narrative, right? We prefer complex explanations, but the universe is simple.
I got one for you. I'd like to hear your thoughts on, right? So a galaxy, right, is defined as a galaxy, is not defined, but when we say galaxy, people think of a galaxy being the matter that is making up a galaxy, something that you can look at, it's a spinning disk with something in the middle with tails, the whole 9 yards. Beyond the space beyond the galaxy is no longer the galaxy, right? The galaxy is defined by its boundaries of matter that makes up the galaxy. Correct? Am I like
you're approaching an extremely important point here, and it's the question of when was this space created versus the space that I'm in, because the galaxy is the thing that in the center there's a furnace creating new stars by this mechanism I've attempted to explain. So the time here and the space here is only 4 billion years old. But there's other stuff that's way older.
Yes. And could even be a reiteration. Okay, so but the universe isn't defined by mass. The
Well, yes, it
universe,
is.
where a
Yes, it
galaxy is defined by mass, the universe is defined by space.
No, it's all defined by mass.
So-
Space doesn't
Okay, so
exist
beyond space,
independently. Okay, think of it like this. Mass exists on a more fundamental level of reality than space or time. And that's the thing that's so effing hard
okay,
to get
you're
our heads
talking
around.
about dark energy and dark matter. You're talking about even no space has matter. Even space,
I'm saying that
even space with no
time-
matter has.
time is undefined in dark matter.
Mhm.
There's no such, because we can't measure the age, because it's always in that same state, which is adjacent to the energetic minimum, right? It can't go to the
Mhm.
energetic minimum because that's absolute zero. Absolute zero has quantum wonkiness that pops it out of it. So it's oscillating around absolute zero. If
Gotcha.
that's sort of,
No,
you're sort of in a
that's not even-
range.
I'm trying to go to another point, but I have to get through the bushes to get to the point. And this is why I love talking about this stuff. Okay, so I agree that space and time, space and
But the point is
are
that mass can exist without
related.
space and time. But mass is able to, when it collapses and crunches on itself and craps out another sun, it can create time. So 4.5 billion years ago, time was created. So there was a thing that happened that turned this soup of neutrons, of really boring neutrons adjacent to the maximum entropy state, it turned it into what we see here now, which is an amazing plurality of 118 microstates of the periodic table. So the way that you understand the periodic table is as a filter for this neutronic mass, which is basically, okay, I don't have it on here. I'm sorry. I'm going to have to pull it up. I'm looking for the distribution of elements. It might just take me a second. I'm sorry. I thought I had this diagram ready to go, but now apparently I don't.
That's fine.
Great.
My main point is when it comes
just give me a
to
second to find
space
it.
being infinite, is space infinite?
That's what I was trying to get to, is that space
Gotcha.
is not infinite and neither is time, because space is undefined in dark matter. What is the location of dark matter? Everywhere. Look up at night in the
Subatomic
sky.
universe.
Anywhere
No?
you see not a star in the night sky, that's dark matter. It's most of the
Yes.
universe. Most of it is not having the elements in it. It just has blackness. It doesn't have any ability to have electric fields or anything. It's just more or less dead, and the only thing operating in it is gravity. Time doesn't exist there, and neither does space, because it's everywhere. It's forever.
So you can pass through it.
We can only get time and space when it undergoes collapse and creates more time and space.
Okay.
It's not
Question.
creating space time. The space time is conserved because all that's happening is matter from super dense region is going to a slightly less dense region. It's escaping because of quantum state exclusion. It's just the mass is the space time is conserved, the mass is conserved, but the time and the space are instantiated the instant that it's excluded. So that's actually why the galaxies that are farther away are older.
If you get into a spaceship, let's say theoretically, you get in a spaceship and you just keep going, how far can you go?
That's a really good question.
No, I'm not expecting an absolute answer. I want your answer, because I'm trying to lead to something that I said on Twitter once, and it's just a joke, really. It's nothing serious, because we can't prove any of this, right? But I just don't see space, and I mean space as in everybody else who understands space, as there is no boundary, right? There is no, even if there was a boundary, it would be a block of, the space is infinite.
The universe has no boundary. The universe has no boundary. Space and time are boundaries. The universe has no boundaries. The universe creates boundaries. The mechanism by which the universe creates boundaries is the exclusion of this hyperdense dark matter. And the boundary is then, this now has a time. dark matter still has no time or space. It just has space-time. But now this little region, the star, it has time. And how do we know it has time? Because as time goes on, elements decay. If time didn't exist for us, we would not be able to observe the elemental decay. Like, this is a predictable thing that elements will decay. And this is actually how we can tell how old the planets are. And I don't know if you know this, but all the planets in our solar system are approximately the same age. What does that tell you?
Yeah, you can reverse. You can reverse that to say that we've been created.
Well, what does that tell you? If things are the same age, what does that suggest?
Oh, that the universe is that old?
No, that they were created in the same
at the same time. Yes, exactly. Not either for the first time or an iteration of it, which that's one of the things I believe.
No, this is observable. You just have to look it up, like the observable deduced ages based on emission spectra of the planets are equal to within error bars. They're not exactly equal, but they're approximately equal.
Yeah, exactly.
You should watch my video with the strange spirally, like loopy thing.
Well, the fact that we have an observable universe tells us a great deal, and the fact that nothing is coming into our universe, everything's escaping from it, which is kind of funny.
No, it's collapsing into itself. It's collapsing into itself. It's expanding into itself into a smaller areas, which like appear to be collapsed, but it's really only a
dimensional object.
Okay, you got to stop cutting me off here. It's only ever expansion into itself. So if you think about it, light just wants to expand forever, but if it reaches a boundary and bounces off it, it's expanding into itself. It's still expanding. From our point of view, we can say, yeah, maybe we've managed to deflect it and it's not expanding anymore. No, it's still expanding. It's just expanding into itself. So focusing is a form of expanding because the nature of the photon is expansion. So when we have matter expanding out of a gravitational well, it becomes instantiated. It has temporal instantiation. It has spatial instantiation. And the periodic table is a cookie cutter. It's a filter, a sieve through which this matter is instantiating. And if we look at the diagram I have right now, do you know what this diagram depicts?
Is that like
screen,
amount of like
distribution of elements, painting over 31 seasons, joy of painting.
Well, what do we notice? What do we notice? What do we notice about this distribution of elements? How can we describe this? If we were going to do a little calculus LARP and we wanted to inscribe this within a function, how would we describe the function? Can we describe this with a function?
Looks like a
what can we say about this series? Is it a bounded monotonic series? What does it look like?
I can't think of the name. I know what it looks like. I just can't think of the name off the top of my head. It's like trying to go to 0 to light speed. It looks like
Are you thinking about damped oscillation, perhaps? Does it perhaps look like a damped harmonic oscillator? Well, that's exactly what it is. And the reason why we have the distribution that we do is because it's a sieve for matter, and it's saying, "Oh, sorry, I'm trying to go back to where I was before," and it's giving me a hard time. But here we go. Here we're back to this is the important one. Bounded monotonic. So what is this telling us? It's just giving us more anecdotal evidence for what we always knew about entropy, is that the maximum entropy state will be statistically most populated. So the minimum energy state. Oh, sorry, this isn't actually the graph I'm looking for. This is some subset, but this is basically what it looks like. I haven't actually found the graph I'm looking for. I'm sorry. I'm just trying to find the effing distribution. This is like elements in trees or something. I'm sorry.
Wait a second. Something else is following a similar model? I mean, how dare the universe it's all just a wave, bro.
How dare the universe be a fractal? I'm sorry, what is it? It's like, it's not distribution of elements. It's like, there's a different word for it. It's proportions of elements.
Neutral. No, it'd be number of protons. That's how we classify, right?
I'm talking about like how much helium there is in the universe versus how much hydrogen.
Oh.
I'm sorry, I'm just like, it really wish I had this diagram right now that I could just pull it up. God damn it. All right.
Oh no.
Finally.
How dare you get asked a question and just go on.
I just wish I had everything ready to go, but there's limits, I guess. But here's your function. This is what it actually looks like. This is the universal proportions of elements. So we have a pattern. It's a little more complicated than the last one, but there's some sort of pattern there. And this corresponds to the amount that you see of each element relative to each other corresponds to their energy. The less energy it has relative to all the other elements, the more of that species there will be. So that's why you have what appears to be a nearly bounded monotonic function. There's a bit of it doesn't have a perfect pattern. Like, as you can see, elements 3 and 4 go off the normal pattern, but that can be explained with the theory too, because that's the level on which electrical and gravity forces are on par with each other. So there's a time where gravity dominates electricity, then they are on par, and then electricity takes over. So anyway, sorry, that's a hugely complicated complicated digression. It would take probably a little bit more time than what we have today to go into all this. That's why I wasn't really sure what you wanted to talk about today, and I was kind of worried it was going to turn into like something harder, to understand. But I know we had originally.
Well, this is the interesting thing. Sorry to cut you off, but it's just, again, like I remember you said you were coming up with your derivation of
derivation.
Derivation. Yes, words are hard. Of Gauss's theorem, and I'm sitting there and I'm like, I realized just when I went to go use a little memes room and grab a delicious beverage, that all of a sudden it's like, wait, isn't this the problem that so many people on the internet and just everywhere have? When you get like 2 or more smart folks, all of a sudden somebody starts saying something, but somebody has so much other information and relevant things that they'll just kind of point it, and then you end up going down a different causal route from where we were. But sometimes we end up, oh God, maybe the Wolfram things are kind of accurate. Sorry.
No, this is how do I
think we need flashcards to just show what we're talking about right now.
This is basically defining the cycle of what our universe is at the moment, because as stars keep blowing up, they create more complex elements, and as helium, as hydrogen,
they're all
created
at the same time. That's what I'm saying. They're all created bang at the same time. This is the sieve. This is telling you the proportions in which they're going to be created, and they're all created as soon as they're excluded. They're created. This idea of things being forged in stars, that is possible, but these things are largely just instantiated when they're excluded from dark matter.
Is that a distribution of elements or like the masses of stars?
That is the relative proportions of elements. So that's basically saying there's more hydrogen in the universe than anything else. And then after that, it's helium. And then you go, the height of the bars is telling you how much there is relative to everything else. Does that make sense?
Cool.
It's abundance. I think the word is the abundance of the various elements. Elemental abundance. The word was escaping me, but I think that's the correct one.
Yeah, just because, like, for a moment there, I could totally see that potentially being like a distribution of like the masses of stars in the universe. Wouldn't surprise me.
I'm going to share the actual title of this because I kind of feel bad that we haven't even gotten to this. Do we want to just quickly go over the Gauss theorem?
Let's go over what we actually said we were going to do. We've teased people long enough. If anyone's still here, we'll actually...
I kind of feel bad about that. Like, I hope the people watching are enjoying it. And if there's more questions, feel free to ask them in the chat and we'll get back to you. But basically, this is like a quantum thermodynamics, basically. So we're invoking the laws of entropy at the same time as we're invoking the axioms of quantum mechanics. And we're getting predictions from that because entropy has the formulation of the law of entropy contains information. And so we could use that information to then extract more information, aka make predictions. So we've got some definitions, an action potential. You can see also like a force. but I don't, you can't use the term force because force is defined relative to derivatives, and derivatives are not defined because of mass quantization. So we have to start over without using any lingo from differential or integral calculus, because on the quantum scale, these things are not defined because they're not that they're not defined, it's that the act of doing a derivative would invoke the uncertainty principle, because a derivative is a measurement. Measurements affect quantum systems. How do we account for that? Kind of hard to do that. So what we have to sort of acknowledge that measurements affect quantum systems, and then sort of like trace around that fact to get super accurate things, even though we know the minute we observe it, we're basically collapsing it. That's where the ideal shapes come in. And they're so powerful because you can reason vis-a-vis the abstract shapes rather than having to collapse your system through observation. So canonical order, that's what I'm calling it. I might change the name. I don't know what to call it, but we talked, remember my derivation of the 14-dimensional universe the other day?
I remember you saying words and showing some funny pictures.
Well, for the people in the audience who are unfamiliar with this proof, if you take the size of a proton, and then that's the smallest observable distance. The largest observable distance is the largest distance between two observable stars. So you have to, take all the stars in the universe and that you can observe, figure out the largest distance between them, and that's your largest observable distance by definition. So the question is, how many times do we need to multiply the protonic size by 10 to get this maximum observable size of the largest interstellar distance? And the answer is 42. So we have a universe of 42 linear orders. But our universe doesn't define linear orders, does it? Space occurs in threes. Your spatial dimensions are entangled. That's why your sphere is maximum entropy shape, not a circle. Not a hypersphere, but a sphere, because it's in three dimensions, So we collapse 42 down to 14 energetic dimensions. And a canonical order is which of those dimensions are we in? So if we're in the bottom, we're at the periodic table. If we go all the way up, we have to get to the fifth one. So multiply the proton canonical order by 1,005 times. Get to human size. To want to go to the top of the observable universe, we've got to do it 14 times. So this is just referencing which level of causality you're zooming in on, because you have to take into account what level you're on, because the entanglement of space and time varies across the canonical orders, right? Maximally entangled at the bottom, minimally entangled at the top. And if you don't take this into consideration, your whole system is just going to fall apart. All right, differentiated waveforms, super important, and what we were talking about a bit earlier about the creation of new stars from dark matter, that's also called differentiation. So it's non-differentiated before it collapses. Before the dark matter collapses, it's non-differentiated, aka the constituent waveforms are indistinguishable. By vis-a-vis gravity collapse, we have a distinguishing. So we're saying it's not just a blob of soupy neutrons, it's now created a star. Since the star has a boundary that can be defined within a particular range, i.e. its edge, it's considered differentiated. And that's very important because it's that very differentiation that creates the space between the hyperdense matter and the new star. That space did not exist before. That time did not exist before. Upon instantiation, space and time, boom, plus derivative attributes, velocity is created. The sun has velocity. Earth has velocity. Those velocities, as subsequent stars are ejected from the same region, those velocities add up. And that's why the farthest away are moving the fastest. So that's how the system predicts redshifting. Back to Gauss's law. For those of you who know physics, you're probably familiar with Gauss's law of electric flux, which is what we're going to deduce here using entropism. So we're going to not use calculus because we know it doesn't apply. If we accidentally use it, we're going to get some wacky divergent results. Immovable object, unstoppable force style, aka gigantic mess of nonsensical results. Planck's equation, super important because it relates the frequency to the energy. So waveforms have qualities like amplitude and wavelength. Wavelength and frequency are inversely correlated by definition. Energy is determined by frequency. So qualities of waveform, geometric object, tell us attributes of the system that are transcendent. Energy is universal currency of work, and so it's transcendent. So we can talk about energy in the microscope, talk about energy on our scale. It's the thing that is fungible on all scales of reality. So this is just basic construction of a waveform. So we got a waveform. What shape's it going to want to be if we know nothing about it, memes?
Sphere.
Perfect. If we know nothing, the naive approximation to a waveform is a sphere. But if we know that that sphere, it's not just a sphere, it's actually a complicated waveform. So we've got an expanding sphere power, but we also have container that it's in. So it's bouncing off the edges of the container. So it's expanding into itself. So it's going to admit some extra attributes than just a pure sphere, aka little waveform, little wavelets. And that's what I've attempted to draw here. So you have a sphere-ish thing, which is more complicated than a sphere, but still fundamentally sphere-ish. It admits a center, which we call the centroid. So the centroid is the more generalized version of what things like center of mass, center of torque, center of gravity, center of electricity, those things are just generalized to centroid. So if you're referring to a centroid, it's always state specific. It's usually pretty clear what you're referring to. Here we're talking about abstractly constructing a waveform and then saying, I assert that the center exists and that the center fulfills these certain qualities. And this is extremely important in physics. It's called the center of mass coordinate transform. There's, being able to transform to that coordinate system allows for you to solve, world's more problems. So this concept is extremely important. So we have that. And then we say, well, it's vibrating. As soon as it gets a stable point, if it's going to emit sub-frequencies, then it has to have some sort of a stable point. Why?
Because of entropy.
No, because a frequency implies that there is a fixed point about which the frequency is defined. In order to define frequency, we need a fixed point. For example, when you draw a sine graph, you have to have 0. That makes sense? Like the amplitude is relative to a fixed point.
You need a base point.
You need a base point. So so if we have non-trivial eigenfrequencies, then we have a base point because the instantiation of the base point, aka node, is what allows for the frequencies to manifest in the first place. Does that kind of make sense? I'm trying to get the idea across that they're the same thing.
This is actually cementing some more things that I've listened to recently, but continue.
I mean, this stuff is really fundamental, but it's also really counterintuitive because we have intuitions that don't necessarily line up with this stuff because we're designed to survive in a very particular subset of big old universe that's built into us. Now we're just using that wonderful brain that we have that was selected for intelligence to go the extra step and say, well, what parts of my own subjectivity are like screwing me up here in my understanding? So when we have these equivalences, those are the things that are easy to get screwed up because when something is literal, like when observation is literally equal to measurement, it's just really hard to make that, to cement the understanding, like you say.
But this is what we see, bro. I gotcha.
Okay, so from there you have, what you do is you take the circle, the green circle on the left. So what you want to imagine is that this here is, you have a 3-dimensional waveform and you're slicing it down the middle, like an apple. Do you know what I mean? Just sort of see it's
I like apples.
It's a 2-dimensional rendering from a 3-dimensional entity.
Right.
Does that make sense?
Mm-hmm.
So from that, what you want to do is you put in these hypothetical nodes, and then you draw a waveform between the nodes, and then you rotate the waveform about the circle. And you get this.
That would
make
be
sense?
essentially the fractal equivalent.
It's not a fractal exactly. It's a geometric
Or
shape.
not a fractal, but it's. I'm not sure if that's mathematically designed that way. I don't know. I was listening and watching a fractal video on the blue 3, brown 1, blue 3, whatever math channel the other day.
It's not that complicated, but you do have to understand that it's happening in 3 dimensions, right? So if you go on the left-hand side, you're looking at a 2-dimensional object, which is derived from a 3-dimensional object, but we're just going to understand it as a 2-dimensional object, okay? Because it's just we can't visualize the big one. The 3D one's just too hard. Like, I don't know if you guys are trying, but I can't do it. It's hard for me to visualize a 3-dimensional vibrating entity. It just looks like shit. Looks like a donut or something.
I won't complicate the point. Continue.
But we can see what this shape is. There's the circle, which is green, and then there's a waveform, which is connected all the nodes.
Right.
With vibration.
And then you would have the different frequencies, and if you can identify the min and max, you've set a bounds of sorts.
Precisely, which is what we've done here. So what I've done is reflected blue in green to get gray, aka, but it's not an actual reflection. You're rotating blue around green. So it's just going out of the page over, and I don't know if you can visualize that, but that's like your overall shape of your waveform model. Hello?
Yes.
Yeah,
yes,
I mean, it's one of those things that you understand inside. Well, this is one of the things that I can understand inside my head, but not when it comes out my mouth.
It's just a model. That's the thing. It's just a model.
I mean,
it's
so
not
think of it like a snake eating its
just
own butt that has freaking 5 mouses in it. You know?
Oh my
you know
God,
I mean?
you're like a poet or something. That's kind of beautiful.
I get what she's saying. It's not just oscillated. It's literally that blue bar is literally rotating around the green, creating a 3-dimensional shape. You just don't see it on 2-dimensional paper. So yeah.
notice how complicated this is. We took a 3-dimensional object to a 2-dimensional object, and we got a 3-dimensional object back.
3-dimensional object, yeah, exactly, like the episode of Voyager, absolutely. When they used a holodeck to make 3D glasses movie theater.
Oh dear.
Yeah, I get it.
I just imagine a little twinkly thing. It's like, oh, it's coming up from all these different points in a particular oscillation fashion.
It's just a model, but we have to understand that this model, because it shows us the wavelengths, it also shows us the frequencies, and the frequencies are what tell us the energy. So the frequencies are important to be able to deduce geometrically, because they ultimately give us the information of the total energy, which is that transcendent variable we're always looking for. So this is just sort of instantiating a boundary. The point of this diagram is to show you that a boundary on a waveform exists, but it's fuzzy. And this is why it's fuzzy. So we're not just saying that it's nothing and it's completely arbitrary because we're saying it's quantum. We're saying that the notion of a well-defined boundary is something that we impose. It's not something that exists objectively. This is closer to what exists objectively. So we have a notion of a boundary. Boundaries are extremely comforting things because it's like, yeah, I sure like the idea that I can distinguish one thing from another. We're essentially contrast detectors. That's what animals are. Just detecting various contrasts that we've learned to detect over the years. But ultimately, reality is waveform, simple constructs. Boundaries come along, but we always have to acknowledge that sometimes we're imposing those boundaries for our own ease of understanding, i.e. using a 2-dimensional rendition rather than trying to generate a 3D accurate quote-unquote rendition. This is so much easier. And I can still access the same information because of energy.
No. To visualize something we can't otherwise see looking at its raw form.
Yeah, you don't want people's heads to hurt.
Standing waveform. So that's your 3D object that we were talking about before. So that 3D object, even though the waveform is constantly vibrating, that 3D object doesn't change. by definition, all it is an it's inscribed inside the boundaries, and those boundaries, sort of the shape can oscillate within itself, but it's not, the eigenfrequencies don't change unless there's energy put into the system or work done on the system.
Mm-hmm.
And that's the standing waveform. So it's that shape that you get from tracing out the eigenfrequencies. So I've got a little bit here talking about the incompatibility of calculus and quantum mechanics. That's because nature is quantized, it's not continuous, and calculus is predicated on the real number line, the continuity of the real number line. So that's an excellent approximation for most things, because most of the time your measurement device is not interfering with your system sufficiently much as to make this not true. So calculus is and always will be our best approximation to a continuous reality, but reality is not continuous. So there's always that little asterisk. So we'll see, if we get further into the system, we'll see how calculus still applies, but it only applies to specific systems, i.e. those systems which are approximately continuous. So when the quantization takes over, i.e. with creation of stars, and that effect is dominating, calculus, you can't use calculus because calculus is predicated on your system being smooth in space and time. So quantization, I don't need to define this again, we've been over it. Quantization is just the idea that things exist in separate stair-step levels rather than in a continuous thing. So our experience feels continuous, our mathematics mostly is continuous, our physics is mostly continuous, but because that's what's intuitive, but what reality is quantized. So we have to go as extra steps to be like, okay, yeah, my intuitions are actually dead wrong here because I'm on the fifth order. I exist on the fifth order, but what about the first order? The first order is the fundamental one. Okay, so we've got a region with n charged quanta bounded by an area in local free space, which is defined as as being fully contained within the total causality, which is the union of all of these canonical orders, where the measurement limit applies on the first order, then it applies on the second, third, fourth, blah, 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 blah. Phi, or sorry, this isn't phi. I don't even know what letter this is. So wait,
how many orders are you saying?
There's 14 in the universe.
Okay.
We're on the fifth. Our minds are on have 11 dimensions though. Pretty epic.
Sweet.
So maybe it's Psi. Could that be it? Do you know how to pronounce this Greek letter?
No.
It's psi,
I don't know.
right?
I don't know what that is.
Damn it.
It's your derivation.
I'm just going with the standard
Oh,
ones.
crap, I'm muted. I'm sitting here talking. Yes, that is Psi. Pronounced S-A-I. That is Psi. Yes.
Psi,
I'm like,
perfect.
you guys hearing me? I'm like, oh
Humanity.
no.
So if we let a charged region be bounded by an area, we are synthetically imposing that area. It doesn't exist without us saying that it's there. So the proof is basically saying that the very act of imposing a boundary on a charge is entropically equivalent to flux in basically keeping with Gauss's law. So we first determine what the waveform is doing relative to itself, and then we determine what it's doing relative to the universe in which it exists. And then we look at the combined action. So law of entropy is just saying that psi is going to spontaneously reconfigure towards a state of maximum entropy or minimum energy. And we won't know what that is till we get there, but we have to sort of have faith that we're going to be able to tell, because we only really have to compare two states, right? Which one is higher in energy? Well, it's obvious. What we've seen a bunch of those so far, like the absolute zero. That's the minimum energy state, right? We know it's obvious. We just have to compare it to the one adjacent to it. So don't be too intimidated.
Maximum energy.
Sorry, it's maximum entropy and minimum energy. I'm sorry if I got those confused, but those are the same thing.
Okay.
So within itself, there's n charges, and they're indistinguishable because the nature of material causality is entanglement, i.e., separation doesn't occur naturally. togetherness occurs naturally. Separation is something that's imposed, either by natural forces, i.e. separation of matter from gravitational collapse, or us, putting a measurement device and doing some sort of separation. The nature of matter is attached because gravity is spontaneously acting at a distance. Everything is stuck together, congealed. So they're indistinguishable because it would take energy to distinguish them. There's a boundary that you've imposed, and so it's going to now occupy a definite spatial geometry. The shape that minimizes the net torque, we've been over this again, is the sphere. So we've got a situation where there's n-charged waveforms, and they're just tending towards the sphere. And you're saying, I'm going to throw a geometric object around them. I'm going to define it as a fixed, as a continuous area, a closed area. Well, so that predicts that we'll get a sphere. Now, what about between the waveform of charged particles and the rest of everything else? The effect of the waveform will be minimized on the universe. And since the charges are the same, the natural reaction to that sameness is expansion, repulsion. Opposites attract, likes repel. We already know that from electricity. This expansion is called flux. So we've just basically equated them because the minute you impose a boundary, you're causing this flux by the very virtue of defining a boundary because of natural entropic pressure that is seeking to constantly diffuse these charges. And so we get back to the Gauss law. Flux is proportional to the number of charged elements. And we get this vacuum permittivity, which is kind of interesting because it sort of gives you a maybe deeper understanding of what vacuum permittivity is sort of the amount of energy, or sorry, the amount of, how would you, let me see here, it's the ratio between the total energy and the flux energy. So how easily can electricity travel through the basic ether, which is space without mass? So I hope that was clear. So it's interesting because you don't have to use calculus for it. But then you can recover the stuff from calculus later on by approximating the expanding waveform as continuous, which you can do because of entanglement. So the electric field is approximately continuous. Therefore, the integral form of Gauss's theorem is valid. It's heckin' valid because there's nothing to deviate this system from behaving continuously because you're not getting uncertainty effects on a boundary of expanding charged waveforms. You have to have very specific conditions to get uncertainty effects, which is what screws up your ability to use calculus.
Right. Well, it would be combinatorial, I would assume, or would that not be the case?
What do you mean by combinatorial?
Basically, you are utilizing entropy to compute this. I would assume that there would be a calculus-based form, like basically whatever parameters you choose, assuming the universe is the same, you would just have to use those same parameters, maybe in a slightly different way, but relative, you would essentially get approximately the same results, more or less. Maybe you're defining something as something different. I thought that was how math worked. Like you express things in different ways.
Gauss was able to get the right answer, not because calculus is true, because his derivation requires the well-definedness of the differential area, which is not well-defined in reality, but because his differential area was on a waveform that was continuous, because he wasn't measuring the particles, he was measuring the waveform associated with the particles.
Okay, so he had a constant. He had a constant. Or a definable term.
He defined calculus correctly. That doesn't make calculus universally true. It just means that because he did calculus on the surface of a waveform instead of on a physical surface, it's exactly right because the waveform isn't subject to the uncertainty effects and therefore calculus is true. because calculus only becomes not true when the waveform is subject to uncertainty effects. Which I don't know if it's clear why this waveform is not subject to uncertainty effects. Uncertainty effects only happens when you have a really sharp measurement device, right? Like a slit, because it's delta x, delta px is less than h.
Because we're on.
There's no delta
scale at
x
that
in
point,
this system.
I'm glad I have the tag at the bottom of the screen.
Because we'd have to, like, if we then decided to take this thought experiment to another level and introduce a slit, well, then we couldn't apply calculus anymore, because the slit is going to screw up calculus, because it's going to bring the quantum nature of the waveform into resolution, into sharp focus.
Oh, our eigenstates would not compute.
Exactly. They wouldn't be computationally equivalent anymore. Now, this is a very important thing, is a computational equivalence. Like your understanding of causality has to have the same computational complexity as actual causality, or you're going to get either not complicated enough, which you're going to recover the complexity on the back end as like infinity particles that just diverge, right? The idea is that we want to avoid divergence. We want convergence in knowledge. We want everything to just be adding to itself. We want all the presumptions to be consistent with each other, because that's the only way to really remember it.
We want to avoid the error
human.
strain.
We are humans. Like, we have to understand we have extremely limited capacities. As smart as we think we are, we're a pile of flesh. We're not, on the same level of complexity as like even the planet, right? Exactly.
Well, we are of the universe,
level.
so I mean, this is the crazy thing, and this is where I think you start getting metaphysical. But for sake of discussion, the fact we've been going on for over 2 hours now, continue.
Oh, but yeah,
I will counter that real. I'm sorry. I just wanted to add one point. I'm just glad the universe is showing that evolution is bringing us higher and higher. So maybe one day we'll evolve to something we're a lot smarter than what we're capable of now.
Got to transcend the super sapiens.
There seems to be a trend.
Crabs are what we're all headed towards.
I thought it was iguanas, right? Or Voyager, right? We're all becoming iguanas or whatever.
Life tends towards crab, but that's another discussion we can have another time.
Yeah, it's been a great chat, and I guess you want to wrap it up now. So I really appreciate.
Oh no, you can finish. You had like another page left. So
no, the extra page was just definitions. I can send you the document if you want to peruse it. We could discuss it more on the show. I actually thought we were just going to be talking about the unified field model, not that particular application of it. So I didn't prepare an actual explanation, but we can go into it more, and hopefully it's something that people find appealing, because I certainly enjoy that satisfaction of, oh yeah, I solved another one, and everything is like, all the axioms are great. You don't have to remember something that feels wrong.
Well, this is the thing. I'm looking at that, and I'm like, all right, I really don't know what most of this means. I realize that Jen's explaining it to me in a way that I can at least attempt to comprehend, but there are certain things within there that you started kind of listing, and I'm like, all right, maybe it wasn't in the exact same state, but mimetically, I'm like, from that video from Dude Man that says that from a hyperbolic knot, he's essentially computed basically all 17 particles and everything.
That's awesome.
Like, this looks similar, and actually, I think I might know why now, just because I actually looked at some of the other YouTube videos that came up when I looked at this. Apparently, and again, I think this is the individual that when he was working at NASA, he may or may not have lost his job for stealing moon rocks for love. That's the title of the CBS video I'm looking at. I think he got caught stealing rocks.
I stole moon rocks for love.
No, I think he literally wrote a book there. It's like something about, that's one of his books, and then he has Tensor Networks that one of the other online field theorists literally was like, oh, I'm studying that too. It was interesting, and I'm just looking, I'm like, all right, the predictions he had, the muon release does kind of steel man that as well. I'm like, it would be kind of cool, because now if we do have a little base source code, what the hell else can we do? Like, if we actually have like accurate predictions, it's like,
because that's the unified field model, because it predicts everything. Its information content is lower, it's simpler. It inherits the status. If it predicts the standard model, it inherits the prestige of it because it's simpler, because it derives from a simpler object.
Well, he also didn't really throw anything out. This is the thing. I'm looking at all the different things. He's using well-established like equations and everything like that. So I'm like, all right, if this makes sense, then depending on which model you use, how can we simplify this down, basically communicating the maximum amount of information the simplest way possible.
And that's the fucking cool thing, is that this might not even be inconsistent with my model.
Well, that's the thing. I'm looking at what you have there, and I'm like, all right, some of these signs and everything, they're looking awfully familiar here. That's why it's like, I think y'all are kind of saying the same thing, just in a slightly different way. That's why I'm like, all right, is it combinatorial? Like, are we ending up in the same place?
It's axiomatic. It's axiomatic because their axioms are slightly different. They got a slightly different answer. But the information, common denominator, what we're going to notice is that whatever that is going to obey the measurement limit, because there's a limit to how many independent things exist in the universe.
Yeah, well, even MC was saying, he's like, well, protons, neutrons, and electrons, they can all be kind of interchangeable and stuff. I'm like, energy, this, that, if energy is a constant, stuff that you can just kind of change its form. I'm like, well, that's very interesting.
Well, think of energy like money. It's a currency of transmission of potential to do work. And what is work? Changing a system. It's a very fundamental thing. We're going to an extremely general level. That's what's hard. It's the induction. It's always the harder step. So what we're saying is that it almost sounds tautological, doesn't it? And that's the real art of it, is to express what are tautological things, but which are also information positive. So it is going to be tautological and simple and short, because that's what the universe is. We're the thing that's complicated. And we're just extracting our own complicatedness from what's actually real.
It's all just a wave, bro. But all right, my Wi-Fi connection was going in a little bit and out. Then it was giving me the little warning. I've never seen that warning before. What a novel thing. But yeah, Jen, why don't you let the good folks know where they can find you? I'll toss your link in the chat below.
Oh, thanks.
So it's over there. Yeah.
Yeah, thanks. So right now, like, I got a channel, and please feel free to reach out, especially if you want to come on and talk and have me answer your questions about how things work. I love going into those, like, whatever questions you have. Anything you've been spending a long time thinking about, the longer the better. That means I'll have more sort of stuff to grab onto, more existing knowledge.
You'll have more disciples at the Church of Entropy.
It always comes down to quantum, right? It's like the quantum transition is fast, but the preparation for the transition is slow. So there's this huge buildup of energy, and then boom, quantum transition. Right now we have this subjective idea that learning is linear, continuous. That's what we have to break. Once we can break that, we're no longer shackled by this false concept of continuous reality. And then we can really start to think, okay, well, how sure am I about what I'm saying? And really be able to, like, actually go back to first principles and talk it all out. So that's what I'm hoping, is to resolve these things people think about, and these paradoxes people have, and answers about consciousness, and just understanding why the questions are themselves so challenging. I really appreciate having a chance to talk about it. And I also have a blog. My most recent article is about the monad, and I had a really fun time writing that one. So I think that's a good place to start for people who maybe don't have a background in math and physics, just to see from a visualization perspective, an ideological, philosophical perspective, however you want to word that, just to see maybe where I'm coming from, because mathematics is secondary, physics is secondary. I have knowledge that is more fundamental than that I am applying to these domains. So if you aren't super familiar, don't feel like it's beyond you. It's really just a logical thing. I really tried to bare bones it into the purely logic domain, And we can introduce calculus later if you want to, but that's a big if. So thanks again, and I look forward to Week in Review. But I will have other streams, but I don't really like to stream alone. I'm just like, I'm more the sort of dialogue type teacher than just the monologue. So that's why right now the only show I have is Week in Review with David, which is progressing really well. And I want to thank Memes for coming on to that too. So if you like Memes content, you can check out the last maybe 3 shows. He's been a great contributor there, and we appreciate that and hope he'll be back. And it was great to meet you. Sorry, I'm not sure what to call you. LDG, Pixels, Geeks, Enjoy Nerdrotica. You're muted.
LDG. LDG is my initials.
Great. It's really great to meet you, and thank you so much for your contributions. And hopefully we can talk again soon.
It's fun to listen to. Always.
Hey, we all like to geek out on science once in a while, no matter what form it's in. But I have Jen's channel as well as her blog in the chat below, as well as LDG's channel right down there for y'all. But hey, anybody that's made it to this point, now we're in the future. Thank you all for watching. Be safe there, everybody. Peace out, and long live the elbow bump. Squirrel.
낮에는 따사로운 인간적인 여자 커피 한 잔에 여유를 아는 품격 있는 여자 오빤 강남